Hello, good morning. Can you hear me?
Good morning. Yes, bro.
Okay. Sorry for today, but I didn't manage to come to the university. But we can for sure meet together next Thursday. For next, so in 2 days I will be able to come back. Okay. For those of you who want to come to the university. Record. Okay. So let me see. Do you see the screen? Yes. So last time I think we started to consider the case of molecules, and specifically we were dealing with diatomic molecules. So something like that we can be modeled as a sort of rigid bar. Well, not actually very rigid in the sense that at some point we, and I will discuss this in a moment, we can include also the possibility for the two masses to actually move with respect to the equilibrium position. So, but what we did last time is to consider this sort of rigid bar, and we said, okay, there are 3n degrees of freedom associated with the translational motion of the center of mass, okay? With the translation of the center of mass. And also we have also estimated which is the typical excitation energy for those degrees of freedom. And we concluded that the typical excitation energy in terms of MeV is of the order 10 to 20 to the minus 23 MeV, which in terms of temperature is of the order of 10 to the minus 13 Kelvin. And this will be important in a moment when we will consider the effect of quantum mechanics on those degrees of freedom. So what we can anticipate, what we will see is that, so basically the translational degrees of freedom are always excited, at least in the case in which we are not considering now correction due to the statistics. Okay, so we are just considering now there will be other correction due to the statistics, so the Fermi-Dirac or the Bose-Einstein statistics. But at the moment, we can just assume that the translational degrees of freedom are excited, basically always excited, okay? Then we said this, okay, the contribution to the energy, to the internal energy for from coming from this translational motion is actually the usual 3/2 kBt, and so it's kBt half times 3n, which are, what are these 3n? We have 3n quadratic degrees of freedom in the Hamiltonian. And each of those degrees of freedom contributes with a kBt. What means quadratic? Means that we have in the integral, we have something like this, dp, we have this kind of structure, e to the minus p squared divided by 2m beta, from minus infinity to plus infinity. So when I integrate this kind of integrals, I get a pi, and I get 2m divided by beta, okay? And actually it's from this square root of beta that actually at the end we find the 1/2 kBt, because when I do the log of this, I get 1/2 log of 1 over beta, and if I do the minus the derivative with respect to beta, I get exactly the kBt half, okay? So here you compute partition function, and then the internal energy is minus derivative with respect to beta of the log of the partition function. And then you get the usual 1/2 kBt for each of those degrees of freedom. Okay, good. Now, at some point, we said, okay, now let's consider also the possibility of rotation. And actually, we have an Hamiltonian associated with the rotation of this rigid bar, which is written in the following way. So the rotational Hamiltonian is 1 over 2I, where I is the moment of inertia. Then we have p theta squared plus p phi squared divided by sen squared theta. And of course, now when I do the partition function associated to this Hamiltonian for one particle, I have to integrate over the degrees of freedom. So apart from the, so we have to integrate over this momenta, but in spherical coordinates now this time. And so we have something like this, which is d phi from 0 to 2 pi, which is the integration over the coordinates, d theta from 0 to pi. Then we have the dp theta from minus infinity to plus infinity of e to the minus p theta squared divided by 2I beta. And then finally we have a dp phi from minus infinity to plus infinity of e to the minus p phi squared beta 2I and sen squared theta. And we said last time that the Jacobian, when dealing with Cartesian and spherical coordinates, but in phase space, the Jacobian is equal to 1. I have not shown this, but it's just a result one can derive in analytical mechanics. Okay, so now I think that we have computed last time this, so you can compute this canonical partition function for one particle, which is associated so with an Hamiltonian, which is associated with the rotation of this rigid bar. And I think that we arrived at this expression, that this is equal to, well, the integral over the angle was done. So there is another Gaussian integral. Here we have another Gaussian integral, so everything is very easy. And also we sketched this derivation last time. And what you get is that this ZC1 associated to the rotation is equal to 8 pi squared. And then I have a I kBt. Okay, so when I do now the calculation of the minus derivative with respect to beta of the log of this quantity, here you have a beta here, I have the usual derivative with respect to beta of the log of beta divided by 8 pi squared I, which is clearly 8 pi squared I divided by beta, 1 divided by 8 pi squared I, which cancels, and then this is kBt. Okay? So now we have indeed two quadratic degrees of freedom. Maybe this is not a very sensible way to explain this, but by quadratic degrees of freedom, I mean that it's quadratic in the coordinate or quadratic in the momentum. And this could be in, let's say, in spherical coordinates or in Cartesian coordinates, etc. Okay, the most important thing is that in the Hamiltonian, I have something like e to the minus x squared. So I have a Gaussian integral, okay? Not in the Hamiltonian, the exponential of the Hamiltonian. So now again here you have two quadratic degrees of freedom, which has the p theta squared and the p phi squared. And therefore we have again twice kBt, half, which in total is kBt. And this will be the contribution of to the internal energy of rotation. Okay, contribution to U from the rotational degrees of freedom. Okay, we will see, so this was expected classically. Actually, we will see later that differently from the translational degrees of freedom, actually, there is a critical temperature above which we can excite the rotational degrees of freedom. Okay, those degrees of freedom are not always excited. It depends on the temperature. Okay, let me change page. And now let's consider also another possibility, which is the following. We have our rigid bar that models the molecules with those two masses here. So we can consider the vibrational degrees of freedom. Vibrational degrees of freedom, which is the possibility that actually these two particles actually move with respect to their equilibrium situation, okay? There are vibration of these two masses. How to describe these vibrational degrees of freedom? Well, introduce an Hamiltonian that I call H vibr, which is the one of an harmonic oscillator. And this harmonic oscillator, for this harmonic oscillator, we know which is the Hamiltonian. It will be a p squared divided by 2 mu. I will say in a moment what is mu. And then I have something like 1 half mu omega squared q squared. Okay? Where mu is the reduced mass, so is m1, m2 divided by m1 plus m2. And omega is a, let's say, vibrational frequency associated with this molecule. We will estimate this, okay? This is a frequency of oscillation. Okay? We will estimate this later. Okay? So for such a Hamiltonian, I think we have seen example already of particles, free particles, which are moving in a potential that is such that we have a potential energy of the type of the harmonic oscillator, and we say that again, due to the usual reason, since those are two quadratic degrees of freedom, again we have two quadratic degrees of freedom. Is not necessary to do the calculation again, and so we will have again twice kBt half when computing the canonical partition function, which will be something like dp dq from minus infinity to plus infinity of e to the minus h vibrational and times beta. Okay, there's no need to do the calculation again. It's always the same. Okay, now let's collect all the info that we have. So we said that U is provided by 3/2 kBt n, which comes from motion, translational motion of the center of mass, plus we have a kBt n coming from the rotational degrees of freedom. Rotational. So this is rotation around the two axes which passes through the center of mass, plus kBt n, which are associated with the oscillations or the vibration of the molecule. So the possibility that those two masses actually can change their relative position. And therefore we have a kBt n again. So in total we have 1 plus 1 times 2, which is 4, so we get 7/2 kBt n. This is the internal energy, and if you want, the heat capacity, which is just the derivative of U with respect to T, is equal to 7/2 kB n. And the heat capacity per particle is just 7/2 kB. Okay? Now, this situation is correct and actually describes the heat capacity or the internal energy of a diatomic gas in the case in which the temperature is large. Okay, this is correct when T is large. When T is large, and therefore we can excite all those degrees of freedom. Okay. We will see in a moment that actually, depending on the temperature, some degrees of freedom are frozen, some other degrees of freedom are instead free to be excited. And this is what we are going to do next. Now, let me change page. Now, what we will try to do is to consider the effect of the fact that we have quantization. Okay, actually, we will see how to describe the canonical ensemble within quantum mechanics will be derived later, but at the moment we can anticipate some result. And in particular, we can write z of c as 1 divided by n factorial v divided by lambda cubed to the power of n, which is just the translation of the center of mass, as usual, as the ideal gas. Then we have a z associated with the rotational motion, which will be to the power of n again, and a z which is associated with the vibration to the power of n. Okay, where those are one particle canonical partition function. I will not write ZC1 rot, otherwise the notation will be very complicated. But you see that those are one particle because they are to the power of n, which means that I am integrating n times the same thing. That's why I have this n. Now let us consider first the vibrational canonical partition function associated with one particle. Now this will be equal to, consider that the energy of a harmonic oscillator is quantized as follows. And therefore here I will have a constant that I will say in a moment what is this constant, the sum from 0 to plus infinity of e to the minus beta h, which is e to the minus beta times h bar omega times n, and where k is just the exponential of minus beta h bar omega divided by 2, which I will not consider, sorry, just a moment. Sorry, but I was waiting for an important call. Now, this k is just a constant, will not be of any importance for what we are going to do later, because we are going anyway to compute the derivative with respect to beta. So this is just a constant, will not contribute. It's if you want, it's the 0 point energy. So we can set this to 0. Well, we can set this to a constant. We will not care about this additional factor. Okay, so now this is k, and then we can make the sum, which is what we have done this many times. So e to the minus beta h omega. Okay. Now we can compute the internal energy associated to the vibration divided by n, which is divided by the number of particles, which will be just minus derivative with respect to beta of the log of this function here. Okay? Where I have put n, I have z vibration to the power of n. When I do the log, I have an n which goes down, and then which allows to determine the energy per particle, the internal energy per particle. Okay, so now I just have to do the log of this and the minus derivative with respect to beta. So I have derivative with respect to beta of the log of this vibrational partition function. So I have 1 minus beta h bar omega. Now you do the calculation and you see that you get the usual function, which we have derived also in another context, Einstein model of a crystal. And so you get this factor here. Now you can also determine the heat capacity per particle, which is the derivative with respect to T of the internal energy per particle. Okay, you just do the derivatives. This we have done this already in the case of the Einstein solid, and you get this function here, Kb. Now let me write this, and I will comment in a moment. T vibrational divided by T squared, and exponential of T vibrational divided by T. And below we have E exponential of T vibrational divided by T minus 1 to power of 2. Where, what is this T vibrational? You see here that I have in the exponential a beta times h bar omega. So if I do h bar omega divided by beta, by kBt, of course, this must be a temperature, and therefore we can indicate with T vibrational this h bar omega divided by kb. Okay? Because for dimensional reason, I have in exponential something which is a-dimensional. Okay, so this h bar omega divided by kb must be a temperature concerning the for what concern the dimensions. And so the heat capacity is this function here, and of course the behavior of this heat capacity was stressed again in the case of the Einstein model of the gas. Now, but we have a scale now to which we can compare. If T is much larger than the T vibrational, what do I get here is that the heat capacity per particle is just, this is 1. This is T vibrational divided by T squared, which cancel with this, and this is just Kb. Okay? Therefore, the heat capacity is just Kbn, exactly as in the case we saw before. So in agreement with the previous classical calculation. So here the energy levels of this harmonic oscillator are quantized before we consider a classical Hamiltonian of the harmonic oscillator, and when doing the integration we can use the Gaussian integral and we get this kBt half. So here instead we are quantizing the levels, but we are discovering that in any case when the temperature is large we recover the previous result, which is the classical result as it should be. What happens instead, let me change page, when the temperature is much smaller than the T vibrational. Now in this case the heat capacity per particle is equal to Kb T vibrational divided by T to the power of 2, and then I get an exponential. I'm just expanding I'm just considering the limit for small temperature of the previous expression. The exponential can in the denominator can be removed, the denominator will just be 1. And you see here that I have an exponential suppression, a small temperature. Okay, so actually this heat capacity per particle is not constant, as I would predict from classical theory, but depends on the temperature. In the limit of large temperature is indeed Kb, is just Kb, okay, the heat capacity per particle, whereas in the limit of small temperature, I have an exponential suppression. Now, what is interesting to do now is try to estimate what is this T vibrational. In order to see which is more or less the temperature above which I can excite these degrees of freedom. And to do that, we will do a back of the envelope calculation that is done can be done as follows. So now consider the potential between the two molecules, between the two atoms in this molecule. Which will be typically, we have described another time this situation, would be typically repulsive at short distances and attractive at large distances. So it would be something like that. For instance, take the Lennard-Jones potential. As an example. Okay. And here you see that we have a scale, which is this R, I call it R0, which is the scale at which we have the minimum of the potential energy. So we can expand the potential U around the equilibrium point, which is the one associated with the minimum of the potential, as follows. U of R, where R is the distance between the atoms within the molecule, and this function UR can be expanded around the minimum, which is U of R0, plus I have a linear term which is vanishing, because it is quadratic. Then I have a plus the second derivative of U with respect to R divided by 2, R minus R0 to the power of 2 plus other terms. Okay. So you see that, okay, this I think you have done this many times, but the leading order, this potential is basically the potential of an harmonic oscillator again, okay, because I have a constant, which is U of R0, and then I have basically a term which is scales as the distance to the power of 2. And what is now this U of R? Now this must be computed exactly at R0. Back on the envelope calculation, we can estimate the second derivative of U with respect to R at R equal to R0 as it must be dimensioning an energy, let's call it E0, ground state energy, divided by a distance squared, and so let's put R0 squared, from dimensional reasons, where now we can fix the scales. Again, these are back on the envelope calculation, and just to fix the scales, but it actually provides results which are within the right order of magnitude. Now, what is E0? This ground state energy, this typical atomic scale. Let me change page. E0 in atomic scale cannot be, of course, MeV, which is a nuclear physics scale, but is of the order of electron volt or some tens electron volt. So let's just make the calculation, fix it to 10 electron volt. Then R0 again, atomic scale or molecular scales. Let's use the Bohr radius, which is equal to 0.5 angstrom. Okay. And also remember that omega for an elastic force is related to the mass and elastic constant by this relation. It's the square root of k divided by m. Therefore, in our case, the T vibrational, which was h bar omega divided by kb, must be equal to h bar divided by kb. And what is omega? If I look at the potential that I wrote before, this omega must be the square root of 1 divided by the reduced mass times the elastic constant, which in this case is E0 divided by R squared, R0 squared. This is because the potential contains a term that was U over R0 plus a vanishing term plus 1/2 U second derivative of U with respect to R computed in R0 and then R minus R0 squared. So you see this function here, this number here is plays the role of the elastic constant. Okay. And this was E0 divided by R0 squared. So by comparing with the standard formula for a classical harmonic oscillator, omega must be this function, must be this number here. Now, okay, good. Now let's work in natural units. And now in natural units, T vibrational should be h bar is 200 MeV times Fermi, kb is equal to 1. Then here you have the square root of 1 divided by mu. Mu is the, let's take the proton mass, but it's a reduced mass, so we take the proton mass divided by 2. So let's take 1 GeV divided by 2. E0 is 10 electron volt, whereas R0 we said is 1/2, so half angstrom, which is 1/4, 10 to the 5 Fermi squared. And I think I have everything. Let me check if I have all the numbers here. GV, 10 electron volt, 1/2, 10 to the 5. Okay, yeah, that's good. Okay, now it's a matter of making the calculation, of course. Let me see if the dimensions are correct. Yes, I have something which is an energy, of course, because Fermi and Fermi cancel. Here you have energy and here you have energy. So you just do the computation and you get this number here. 6 times 10 to the minus 7 MeV, which in terms of Kelvin is of the order of 6 times 10 to 3 Kelvin. Okay. Now this is the typical temperature that you need to reach in order to excite the vibrational degrees of freedom. Okay. Temperature scale to excite the vibrational degrees of freedom. Okay. So when we are at much larger temperature, those degrees of freedom are automatically excited, and then we get we obtain the classical result for the heat capacity per particle or for the internal energy. When we are below this temperature, the effect of quantization starts to play a role, and therefore we have this exponential suppression of those degrees of freedom, and therefore also suppression of the heat capacity. Okay, now we will do the same for the rotational degrees of freedom, which now will be treated within quantum mechanics, although I have not shown, but will be shown later, that the canonical partition function in quantum mechanics has basically the same shape as in the classical one, but that for in quantum mechanics, of course, the Hamiltonian now is an operator, is not just a function of QMP. So it's a more complicated situation. But so now let's deal with rotation. Okay, so now the Hamiltonian, as I said before, is quantized. Sorry, the Hamiltonian is an operator, and the rotational energy is quantized. And we can write these eigenvalues of the Hamiltonian associated with the rotation as follows. The h squared divided by 2I, and then I have here j times j plus 1. Okay? So this is quantization of angular momentum, and therefore also energy. In quantum mechanics. So this must be compared with the standard formula for the rotation, which is 1/2 I squared omega squared, or if you want, is the angular momentum squared divided by 2I. Okay. So the classical case would be here, angular momentum squared, so like L squared. Sorry, L squared. So this will be L squared divided by 2I. And this will be the classical energy associated with the rotation, okay? So just to check that the dimensions are correct. Okay, so now as before, we compute the canonical partition function for one particle, and which is associated with rotation now. And we have this case the sum from J0 to plus infinity. Here I have a degeneracy, which is 2j plus 1, degeneracy, which amounts in summing over the values of m, of the magnetic quantum number m. And then I have exponential of e to the minus beta, and here I have to put the previous formula, which is h squared divided by 2I, and here I have a j times j plus 1. Now, as before, let me introduce a scale of quantization, which will be called now T rotational, which is h squared divided by sorry, here I have I is not the temperature here, otherwise it's a problem. So h squared divided by 2I and kb. This must be a temperature for dimensional reason. So let's define this temperature as being h squared divided by 2I kb. And therefore here we have the sum from J0 to plus infinity of 2j plus 1 e to the minus beta. And here you have the ratio between the two temperatures. So T rotational divided by T. And I have not beta anymore, sorry. But I have a j times j plus 1. Okay? So just to introduce a scale for the temperature as we did before. Okay, now this is the partition function when considering the quantization of the angular momentum. Now in this case we cannot we cannot provide the sum of this function here differently from the case of the harmonic oscillator, but we can do some approximation, at least in the large temperature limit and in the small temperature limit. So first of all, So this is the correct formula. Now we will try to approximate this for large temperature and small temperature, 1 and 2. So let's see what happens. Let me change page. Now, when the temperature is large, for large T, the difference in energy will be small. So let's say that delta E rotational is small because it scales as 1 over T. Being basically the difference between the energy of associated with a certain quantum number J and the quantum number J plus 1, but this case as 1 over T, and therefore for large temperature this excitation energy delta E is small because it scales as 1 over T. And therefore we will actually see that we can instead of summing, we can do an integration. So substitute the sum on J with an integral. But before doing that, we have to do a little trick. Let's call xj, let's define xj as j plus 1 divided by t. And let us compute delta xj as a sort of average as follows: 1/2 xj plus 1 minus xj plus xj minus xj minus 1. What I'm doing here is to consider the variation. So since I have quantized levels here, and which are labeled with j, so they are determined by the discrete values of j, let me consider delta xj, which is the delta that we have in the exponential, okay? The difference in the argument of the exponential. And let me call delta xj the variation of this xj. And let me write delta xj as xj plus 1 minus xj times the same thing but divided by 2. This little trick will allow to make a very interesting simplification. Now, by introducing the definition of xj, this is 1 divided by 2 times the temperature, and then, of course, this will be removed. So I have j plus 2 times j plus 1 minus xj minus 1, which is j minus 1 times j, which will be equal to 1 divided by 2 twice the temperature. Here you have a j squared plus 2 plus 3j minus j squared plus minus j squared plus j plus j. Okay, so j squared can be removed. 3j plus j makes 4. And then I have a plus 2. And so I have an 2j plus 1 divided by t. 2j plus 1 divided by t. And this is delta xj. Okay. So now the canonical partition function for one particle associated with the rotation was, let me write it again, the sum from 0 to plus infinity. Here I have a 2j plus 1 of degeneracy, but 2j plus 1 now is delta xj times t. And here in the exponential, I had a minus t rot divided by t times j plus 1, which can be written in terms of xj times t rot. Okay. Okay, let me first write it, sorry. Let's do it in the following way. T rot divided by T. But this quantity here, j times j plus 1 divided by t, is just xj. Okay, so this is the sum j 0 to plus infinity of t delta xj e to the minus xj t rotational. Okay. Now, as I said before, if t is large, I can replace the sum with an integral and therefore make the following approximation to this canonical partition function, which will be an integral from 0 to plus infinity of t delta xj becomes t times dx. And then here I have the exponential of minus x t rotational. Okay? Because this delta xj, of course, is small, and therefore the sum will approximate actually an integral in dx. Okay? And okay, now this can be done. This is just temperature. Here you have the exponential of minus x t rot, which will be itself divided by t rot, computed from 0 to plus infinity. I adjust t divided by t rot. Okay. Now, if I do the minus derivative with respect to beta of the logarithm of this partition function, I have the minus derivative with respect to beta of the logarithm of t divided by t rot, t divided by t rot. Let me put a kb here, a kb here, so which is just will be minus derivative with respect to beta of 1 divided by beta and kbt rot, okay, which is equal to minus derivative with respect to beta. I have a log missing of the log of beta kbt rotational, which at the end, of course, will provide the usual kbt as before. Kbt as the calculation of before with classical Hamiltonian. So I am, let's say, sure that this result derived from the quantization of angular momentum and therefore rotational energy in quantum mechanics provides the same result, at least in the large temperature limit, because it's exactly the same result we obtained before with the classical Hamiltonian associated with the rotation of this rigid bar. Now, what happens instead in the case of small temperature? Let me change page. For small temperature, I cannot derive an analytical formula for this, but we can at least make the following. This was the sum from j0 to plus infinity of 2j plus 1, and here you have e to the minus t rot divided by t and j plus 1. So let's just consider the first two terms of this sum. So the first one will be just 1, and the second one will be 3 plus 3 e to the minus t rot divided by t times 3 times, this 1 times 1, times 2, j plus 1. Okay, plus other terms. Okay. So let us neglect all the other terms. What we will get is an exponential suppression. I can anticipate you as the case of before. So let us compute in any case. Let's stop here. And well, let us compute the minus derivative with respect to beta of the log of z rotational, which will be, once you do the calculation, will be the following formula. It's just making a derivative, and I can just quote the final result, which will be the following: twice t rot kb times the exponential of minus twice t rot beta kb, and then at the denominator I have 1 plus exponential minus twice t rot beta kb, which is of course 1 divided by t. Okay, so okay, so it's just, if you want, this is just twice t rot kb, and then I have okay, twice t rot kb e to the minus t rot divided by t, and 1 plus e to the minus t twice t rot divided by t, and here I have a factor of 2 also. Okay. And then you see that here for small temperature, again, we have an exponential suppression. Okay, exponential suppression for small temperatures. So again, the classical calculation was correct in the large temperature limit, whereas at small temperature, now we will see how small, we have the correction due to quantum mechanics. Okay. The quantization of levels start to play a role. Now let us estimate, as before, the temperature at which these rotational degrees of freedom are excited. This was h squared divided by 2I kb, and let's do the calculation again in natural units. Where h squared is the usual 200 MeV Fermi squared, kb is equal to 1, then I have a 2, and then I have a moment of inertia. And for the moment of inertia, let us consider the following: 1 GeV as a scale, as a mass scale, 1 proton, and here let's put a distance squared, which will be of the order of, again, 1/2 the angstrom. So is, sorry, yeah, so it's the Bohr radius. Let's put the Bohr radius again. So to the power of 2, and so this is 10 to 5 Fermi squared, and times 1 divided by 4. And yeah, I think that's it. Yeah, the dimension of this will be an energy, of course. So now you put those numbers, you make the calculation, and you finally end up with this number here: 8 times 10 to the minus 9 MeV, which is in Kelvin is about 80 Kelvin. Okay. So now we can make a qualitative plot of the heat capacity per particle, which will work as follows. So suppose that here I have the temperature, and here let's plot CV divided by N, the heat capacity per particle. Now in the large temperature limit, I should get 7.5 kb. So here, this will be the limit for large temperature is 7.5 kb. Then, of course, when the temperature starts to decrease, I will see that the heat capacity will decrease. Then I have another plateau. Then it will decrease again, and then I will have another plateau, where this plateau here corresponds now to 5.5 kb, and the first one to 3.5 kb. And what are the reason for which we have this plateau separated by these drops of the heat capacity? Well, those are the typical scale at which, a temperature scale at which rotational and vibrational degrees of freedom are excited. Now, we said before that translational degrees of freedom are excited already at a temperature of 10 to the minus, 13 Kelvin. So therefore, I always have those degrees of freedom excited. This is because the box on which we are normalizing our wave function is large. Then after that, we will encounter T rotational, which we said it is of the order of 80 Kelvin. And at this point, the heat capacity per particle will increase until it reaches a plateau. This plateau, which corresponds to 5.5 kb, in which I'm adding 2 more quadratic degrees of freedom. And finally, at a temperature which is T vibrational of the order of 10 to, it was I think 6, 10 to 3, 6 times 10 to 3 Kelvin, I finally excite the vibrational degrees of freedom, and so at some point I will reach another plateau, which is this classical plateau at 7.5 kb, okay, as heat capacity per particle, okay? So that's an example on how the canonical partition function, although we have used some formula that we still have to justify fully, but can be used also when dealing with non-monatomic particles. So in the specific case, we are dealing with diatomic particles. We can do the calculation classically by considering the Hamiltonian associated with translation, rotation, and vibration. And classically, all those degrees of freedom are quadratic. Therefore, it's a very easy computing. It's a very easy calculation. Each quadratic degrees of freedom contributes with a kBt half. But also we can, by using the canonical partition function and by basically borrowing this canonical partition function, borrowing the same shape, and by using instead quantum mechanics, so the quantization of angular momentum and the quantization of the energy level of an harmonic oscillator, we can derive both the classical limits, and we discover again the classical limits, but we can also estimate which are temperature under which or below which those degrees of freedom are excited or not. Okay. A full justification of the formula that we have used will be given, well, I don't know, maybe not next week, yeah, maybe next week, when dealing with the quantum ensembles that we have not yet done. And so let me stop for say 5 minutes, and then we will continue, unless there are questions. So let's stop for a few minutes. Ok, ci siamo?
Sì, prof.
Grazie. Allora, procediamo. Qua. Allora, adesso complichiamoci un po' la vita e cominciamo a vedere, noi faremo diciamo solo un caso semplice di una situazione in cui introduciamo l'interazione tra particelle. Quindi per adesso abbiamo visto particelle libere che possono essere libere di muoversi in un volume V, quindi abbiamo diciamo, il Boltzmann counting, eccetera, eccetera, il gas ideale. Abbiamo visto queste particelle, abbiamo visto diciamo, diciamo, sistemi in cui invece le particelle sono localizzate nello spazio, di fatto il volume neanche c'è, ma sono distribuite secondo dei livelli energetici, quindi sono indipendenti tra di loro. Poi abbiamo visto i casi di particelle che appunto hanno anche la possibilità di essere soggette a un campo esterno, un campo gravitazionale, un potenziale tipo oscillatore armonico, un potenziale trifugo. Abbiamo visto anche poi i casi, diciamo l'ultima lezione, di particelle non monatomiche e quindi particelle che possono avere dei gradi di libertà diciamo rotazionali e vibrazionali. Adesso quello che facciamo è di introdurre le interazioni nel canonical ensemble. Quindi interaction between particles in the canonical ensemble. I forgot I'm speaking English or Italian? No, English, of course. Okay. Now let's start with the canonical partition function. So we are classical, so we are not considering quantum mechanics. We will deal with quantum mechanics next week, probably. Now let's write again the canonical partition function for a system of n particles free to move in space, but this time, which is also as the possibility, we are considering the possibility of interaction between particles. So we have the standard normalization, then the Q1, dQ3n, dP1, dP3n, and here I have the exponential of minus beta times a certain Hamiltonian that is a function of Q and P. Let's write the Hamiltonian as follows. Hamiltonian will be the sum from I to n of pi squared, well, let's do 3n, pi squared divided by 2m, which is the kinetic term, plus, and here we have the interaction now, sum from I less than j less equal than n of a certain function of u, which is a function of rej, where rej is the difference in coordinates between the position of particle I and the position of particle j, where ri is the three r corresponds to the three numbers q I x, q I y, and q I z. Okay. I will come back. So here is written in terms of canonical variables, of the canonical variables of analytical mechanics, whereas this is the vector notation for the position of the particles. So this is a potential of interaction between particles. Of, in particular, two particles, because I have this potential depends on Rij, which is actually, let's take this already, the modulus, the absolute value, the modulus of Ri minus Rj. So this potential depends just on the mutual distance between two particles. It does not depend on the single or the position of the single particle, because we do not have any external field. So there is no, there is translational invariance. Okay. Now this is the potential of interaction, and let me see how to write in a slightly different way. Well, actually, it's already fine. This is the potential of the interaction that I will assume it depends just on the mutual distance between the particle. Okay. Now, of course, the difficult part here is computing the integral over the coordinates dq1, dq3n, because the exponential now contains a function of u, which it could be a very complicated function. Okay. But in any case, we can factorize z of c as follows. I will have a contribution which is the z of c of the ideal gas, which comes from integration over p, from the integral on p1, p3n, times another partition function that I will call z of u, in which z of u is the contribution to the partition function, which is related to the integral over the coordinates of the potential energy, of the, well, the piece of the Hamiltonian containing the potential energy. Okay, so this will be, let me indicate dq1, dq3n, and here I have e to the minus beta sum from I less than j less than n u of rij. Let me comment a moment on this sum. In this sum, what I'm doing is that the i's must be different and smaller with respect to j, and this is to avoid double counting since u of rij is equal to u of rji. What is important is just the mutual distance between the particles. Okay, so in this fashion, I is smaller than j, and j runs from 1 to n. I can be sure that I just consider once the interaction between two pairs of particles, and I do not have a double counting. Okay, this can be written also in this way. Let's collect the three numbers associated with the position of a particle in just a vector, and so we can indicate with dr1, drn of e to the minus beta, and then the sum from I less than j less equal than n u of rij. Okay, and this is the z of u, in which I have just collected the three numbers of the coordinates in just one vector, which is the position vector. Now, clearly, if u is equal to 0, so in absence of potential, well, actually, let me be more, actually more precise. Let me be more precise. Actually, this one is the ideal gas contribution. Oh, ok, aspettate che questo qui. Okay, let me write in the other page. As I wrote before that Z of C is the Z of the ideal gas times Z of U, but actually, please correct this sentence before, this is divided by V to the power of N. So it's not exactly the canonical partition function of the ideal gas, because I'm just integrating over the momenta. Okay, so therefore there is a V to the power of N. Let me correct this also in my notes. And indeed, of course, if you sorry, maybe I'm making a mess. Sorry. Yeah, it's okay. I think it's okay. Yeah. Indeed, if the function u is equal to 0, the z of u for what we have written before is just v to the power of n. And therefore, we get that in this case, the canonical partition function is just the one of the ideal gas, where the one of the ideal gas, I remind you, was 1 divided by n factorial v to the power of n and lambda to the power of 3n, where lambda is the de Broglie wavelength. Okay. Now, so for the ideal gas, I just remind you that at some point when introducing the Helmholtz free energy, which was minus kBt, the log of the canonical partition function, we can derive thermodynamics, and in particular, at some point, we arrive at the classical equation for the ideal gas, which is P divided by kBt is equal to n divided by volume, which is equal to the density for ideal gas. And now the fact that we have another term here, which in principle is different from v to the power of n, modifies the previous equation of state as follows. We can show, and we will see this later. We can show that in presence of interaction, the previous equation must be modified as follows. P divided by kBt is equal to the sum from J1 to plus infinity of Cjt times n to the power of j when n is the density, which is C1, with C1 is set to 1, is just n plus C2 n squared plus C3 n cubed plus etc. This is called virial expansion. Virial expansion of the equation of state. So basically, this expansion basically tells you that the ratio between P and kBt is equal to density of leading order, so without interaction, not a leading order, but without interaction, plus other terms which are in powers. There is a hierarchy of correction which scales as n to the power of j. Each of those n is multiplied by some function C2 and C3, which are the virial coefficients, which in general are function of the temperature. So therefore, the equation of state looks more complicated in the sense that we do not have anymore P divided by kBt equal to the density, but we have the density plus the density squared times a function which is a function of t, etc., and all the other terms. Now, what we will do is to prove actually that the first correction to the ideal gas is a quadratic correction to a correction which is quadratic in the density. Let me change page. We will prove that the first correction to the ideal gas is quadratic in density, and will actually compute the function C2 of t, which is the virial, the second virial coefficient. Okay, so this is the role, the aim of this lecture. Is introducing interaction and see how interaction modifies, well, at leading order in density, the equation of state of our system of particles. Okay. Okay, so let me analyze a little bit the term that we have in the Hamiltonian, the potential part of the Hamiltonian. At some point, we have an exponential e to the minus beta, and then we have the sum. No? So we have the sum from I less than j less equal than n of u of, let me call it ij, where u of ij, just to make the notation easier, is a function of u as computed in R of ij. Okay. Now, this is equal to, let me single out the interaction between all the particles with particle n. So this will be equal to u1n plus u2n plus un minus 1n plus I have another sum. Let me call it sum prime of uij, which contains all the other terms. In another way, said in another way, I less than j less than n, not less equal. This sum will be will not include the interaction of the particles with particle n. Okay. So when I do the exponential of these, so I have e to the minus beta sum from I less than j less equal n of uij. I can therefore write this exponential as the product of two exponential, which is the beta sum I less than n of uin, where I'm again singling out the interaction between all the particles and particle n times e to the minus beta, the sum prime of the uij. Okay. Now this function here will not depend, or does not depend, on the position of the n particle. So it does not depend on Rn, because here we have all the interaction between all the particles but for particle n. Whereas this function here, this depends on Rn, but it also depends on R1 and R to the n and Rn minus 1. Okay, so let me go on and okay, let me change page first. So we want to compute, well, actually to approximate this partition function, the factor of the partition function which is associated with the interaction. So z of u is equal to integral dr1 and drn of exponential of minus beta sum from I less than n of u in, and then the exponential of e to the minus beta, the sum prime of u ij. Now let me write e to the minus beta sum from I less than n of u I n. Let me write it in the following way for a reason that will be clear later. 1 plus the exponential of minus beta sum I less than n u I n minus 1, where I just added and subtracted 1. In this way, the z of u is equal to, let me factorize all the integrals on the position of all the particles but for particle n. dr n minus 1, therefore. And then I have the exponential of minus beta sum prime of uij, where, as I said before, this exponential does not contain the dependence on Rn. So here I just add the Rn, and then we introduce this one plus e to the minus beta sum I less than n of u I n minus 1. Let me see if I have all the terms. dr1 blah 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 minus 1. Okay, good. Okay, this is now equal to the integral from dr1 drn minus 1 e to the minus beta sum prime of uij. Here we have the integral drn of 1 is just the volume, v, of the box, if you want, plus, let me call it w, where w is this factor here, is the integral drn of the exponential of e to the minus beta sum I less than n uin minus 1. Okay. Now the thing is that we have to compute, well, to approximate this function w, because this is the complicated part. But we can see that we can approximate this function, and we can motivate, we can provide some motivation of this approximation, at least in the limit in which the density of the particles is small. Indeed, what I'm going to compute is basically a correction for the ideal gas due to the interaction, and the ideal gas equational state was varied indeed in the approximation of small density. So what we are going to do is to provide the first correction to the ideal gas, which is in any case is already based on the approximation of small density. Now, W is actually a complicated function of Rn, but also of all the other coordinates. What we will assume is actually that W is assumed to be on Rn, but not on R1 minus 1. So we will assume, and we will provide, of course, an explanation for that, that this W, this function, is actually a function of just Rn, and does not depend instead on the other coordinates, or it has a mild dependence on the other coordinates. So to motivate this assumption that we will do in a moment, let's make a plot of the integrand of this function here. Let me change page first of all. Let's call I this function here, e to the minus beta u of I n minus 1. because in the integral of w, so in this w function, I have always integral of this fashion, of this form. I have an integral that contains the exponential of the sum. So let's analyze each of these terms, and let's see how this function behaves well, as a function of r. So let's make a plot. So I, as a function of r, it has the following behavior. Now, this is a function of r, which in this case is ri minus rn modulus. And what happens when r goes to 0? When r is going to 0, u becomes large and repulsive. Because typically the potential u, it has the shape that we also reminded before, that to be repulsive at small distances and to be attractive at large distances. So when r is going to 0, u becomes repulsive and large. Well, it actually explodes, and therefore this term will tend to 0. So this function e will tend to -1. Okay? Then what happens at large distances? At large distances, u is attractive and small. So therefore, when this is small, and this is attractive and small, let me check what happens. So when r is large, wait just one moment because I'm getting lost. So for r going to 0, u goes to plus infinity and I goes to -1. That's okay. So it goes in this way. When the potential, when going to infinity, the potential grows and becomes repulsive. So I have that actually this goes up and will become positive because the potential is attractive. It is attractive when the distance is large. Okay, so then it will become again positive, this integral, because the exponential will grow, because u, it has a negative sign, and then it will grow. Okay, and then what happens when r is going to infinity? When r is going to infinity, this will go to 0. So something like that. Because when r is going to infinity, the exponential of minus beta u goes to 1, and therefore 1 minus 1, so this in goes to 0. So typically, this function here, it has the following shape. It is -1 in the limit of r small. It goes to 0 when r is going to infinity, and will actually increase for a while as due to the fact that the potential is repulsive at short distances and attractive large distances. Now, this is to say that basically the potential at some point, at some scale, does not exist anymore. So the potential, well, not the potential, but also the I function drops to 0 at a distance which is of the order of the intermolecular typical scales, no, of the interaction at a distance, let's say d, related to the interaction okay. So I mean, in other words, if two particles are very large, have very large distances and can neglect the contribution to the potential and to the total potential energy of those particles. Whereas if the two particles are close to each other, this function I is equal to -1. And then, okay, for intermediate distances, I have a shape like this one, okay? So now this is to say that when dealing with a system of many particles in presence of interaction, I can figure out what's going on in this by making this sort of plot. I have particles 1, particles 2, particle 3, 4, and then at some point, since I'm considering the interaction between a generic particle with the particle n, I have n here. So at a certain, let's say, t equal to t star, let's consider this situation to be the following. Now you see that in this situation, the only contribution will become to the potential energy will become to this, from this interaction. See, the only contribution to Z of U. Well, actually, the only contribution in the sum, let's say in the sum I less than n of U I n. If n is very close to 1 and is far away from 2, 3, 4, and n minus 1, in this sum, basically what I will have that it will dominate just the term 1n, okay? Which is basically the fact that at small density, this is true at small densities for which only two-body collisions or two-body interactions are important. Now, if the density instead is large, I can have a situation in which particle 1 and particle r are very close, but also particle 2. And then in this case, I have all the interaction that must be taken into account between particle n, between particle n, particle 1, particle n, particle 2, etc. Okay? So it's somehow easy to realize that what we are going to, the approximation that we are going to consider are valid under the hypothesis in which the density is small, because in this case I can, if you want, count the interaction between particles with pairs, pair by pair. I can count the contribution to the total potential energy from these particles, okay, from the interaction between two particles and not of many particles at the same time. Now, if I look at this integral, and then I think I will finish for today. Devo prendere un'altra paginina. Let us consider this integral. Let me change page. I have the integral of dr n of e to the minus beta sum I less than n of u I n minus 1. Now this integral must be an integral over the total volume. Let me be more clear on this, which is the volume of the box. Okay. Usually I'm not making this dependence on v explicit, but when doing the integral, just write b to the power of n, for instance, okay? Or for each particle, I have a factor of v. Now I have to integrate over all this volume here, and suppose that here we have the particle n, particle 1, particle 2, particle 3, etc. Now, if you want, I can do, for what I said before, I can separate this integral in several integrals in which I consider the volume associated with the interaction between particle n and particle 1, and here I will have just the contribution drn of e to the minus beta u1n minus 1 plus the integral over the volume vn2 of drn and same function e to the minus beta u2n minus 1 plus all the other terms. Where what I'm doing is the following. I'm separating the total volume in volume, if you want, that are around the volume, that are very close to particle n and particle 1, particle n and particle 3, so something like this, like a cluster, okay? And when considering those clusters, I can neglect the interaction of particle n with all the other particles, but for 1 or 2 or 3, etc. Okay, because being there and the other particles far away, the contribution to the sum will be vanishingly small. Therefore, I can somehow factorize or add each by each all the interaction between particle n and all the other particles. Okay. Now, of course, there is nothing special in particle 1, particle 2, etc. And actually, this integral will be n minus 1, which is all the possible way to combine particle n with the n minus particle, times the integral of d on drn of, for instance, the interaction between particle n and particle 1, but in this case, actually, this is not important. U1 minus 1, okay? Okay, on this approximation, I will comment because it's a little bit tricky next time, but basically the thing is that we can basically assume that the particle n interacts once with particle 1, once with particle 2, so then all these interactions are basically the same, and therefore this integral will be n minus times the same integral, which is this one, which can be written also as an integral in dr of e to the minus beta u of r minus 1, because at this level it's not important to label the particle anymore. But okay, let me stop on this because I want to make this point more clear next Thursday. Okay, so let me stop here for today. So let's meet us in the department in 2 days. Okay. Bye bye.
Arrivederci,
Arrivederci, prof.